Let me try to finish this chapter, all right? What is it about? Inference, right? Inference. Okay, last time I finished here. Say here, this is new topic, okay? Because right now the hypothesis involves two coefficients together, which is beta 1 and beta 2. Before, we only test one beta, right? So right now, actually, we are testing about a linear combination of the parameter. And this is the possible statistic, which is T ratio, okay, the formula. What is the formula here? Beta 1 hat minus beta 2 hat divided by SE, beta 1 hat minus beta 2 hat. So the problem is that the denominator here, how we get SE? We square root the variance, right? So we square root the variance, basically. But the problem is that in order to calculate the variance of beta 1 hat minus beta 2 hat, we need to know the covariance of beta 1 and 2. But this doesn't show you in your regression output. So what do we do? Okay, so this is the problem in general. In general, variance A minus B doesn't equal variance A plus variance B. Because there's a covariance term, okay? Our regression output usually doesn't give us that directly. So next night, there's a trick to solve this problem, but here I want to show you that what is the variance of A minus B? It should be equal to variance A plus variance B and minus 2 times covariance, okay? Say over means covariance of A and B. This is the true formula, okay? And this term, covariance A and B, this is the problem. Because regression output typically reports each coefficient's variance or SE, okay, each one individually, but not the covariance between beta hat 1 and beta hat 2. So we cannot just plug SE beta 1 and SE beta 2 into our formula. We need the cross term as well, which is the covariance, okay? So let's see how we solve it. Right, this is the problem that I just mentioned. Standard error of beta 1 hat minus beta 2 hat. Okay, we got it from taking the square root of the variance, beta 1 hat minus beta 2 hat. But the variance of two coefficients are equal to variance beta 1 hat plus variance beta 2 hat minus 2 times covariance beta 1 hat beta 2 hat. This covariance usually not available in regression output. That's why how to solve it. This is the trick. Instead, okay, we don't test the hypothesis, which is beta 1 minus beta 2 equals 0. Instead, we test, okay, we define theta. We define theta 1, which equal beta 1 minus beta 2. And then we test our hypothesis, null hypothesis H0. Theta 1 equals 0 against our alternative hypothesis, theta 1 less than 0, okay? And let's see our equation here. Log which equal beta 0 plus. This is beta 1, right? Because you rearrange here. Beta 1 equal theta 1 plus beta 2. So basically, this one is our beta 1, right? So right now our regression becomes beta 0 plus beta 1 plus beta 2 GC plus beta 2 universe plus beta 3 experience plus mu. And then you rearrange it, all right? Theta 1 GC plus beta 2 GC plus universe. This is our new regressor. What is GSA? 2 years of education, right? You go back. GSA, 2-year college. Universe means 4 years of college. So right now, this is our new regressor, which means the total year of college. Which means 2-year plus 4-year combined, right? So notice the trick. We're gonna run this regression instead. We're gonna run this regression instead. Use GSC and GSC plus universe as our two regressors, right? X1, X2, and the coefficient on GSC, this is the theta 1 directly. And it's exactly the beta 1 minus beta 2. Okay, you back to our hypothesis. Okay, you back to our hypothesis here, which is theta 1. And its stand error, so SE theta 1 hat. This will comes straight from the regression output, okay? So we don't need any covariance needed. This is the rearrange trick, okay? So basically, right now, our test becomes H0 theta 1 equal 1, okay? Using an ordinary single coefficient t-test, okay, same as always, okay? We turned a hard two coefficients problem into an easy one coefficient problem just by relabeling variables, okay? Relabeling variables. Very handy trick. Remember this one, it comes up again and again in applied work. Let's see the trick applied, okay? Suppose now we run the regression and then we get the answer. This is our regression output. Again, you have to be able to read this regression output, all right? Let's see. Beta 0 hat, beta 1, this is our theta, right? Basically, this is our theta 1 hat. And this is our new regressor, which is the total year of college, all right? Be careful here. This is our new regressor. Let's see the coefficient on GSE, which is negative 0.0102, right? This is our theta 1 hat, which equals what? Theta 1 hat equals beta 1 hat minus beta 2 hat. All right, you go back to our hypothesis. What's its stand error is here, right? In the parentheses, straight from the regression output. So now it's available. We don't need any covariance term. Okay, so I'll let you try to expand those by yourself. Okay, n and r squared, this is from the regression output as well. How about the t ratio? And then we have our p-value here, right? What does it mean? And here is our confidence interval. You should be able to explain each. Okay, I'll give you 2 minutes. And then I'm going to summarize for you. How you get the T? How you get the T ratio? What does the P value mean? How to calculate the confidence interval? Right here is 1.96. And what does it mean? This confidence interval. Get your slides ready. You have a lot of chance to play your phone, to play your iPad. Okay, don't do it. We will have a task. Okay, so T ratio, right? You use the coefficient divided by its standard error, which is negative 1.48. And the P value, which means the probability the T ratio is less than the negative 1.48 equals 0.07. In this case, what does it mean? We cannot reject our hypothesis H0 at 5%, but we can reject it at 10%. Okay, that's why I showed you here. Hypothesis is rejected at 10% level, but not 5% level. So basically, this p-value is 7%, right? That's why you compare with our critical value, 10% and 5%. Okay, let's see the confidence interval. Okay, how to calculate it? Coefficient plus or minus the critical value times the standard error, which is here. What does it mean? Notice that 0 is just barely inside this interval, okay? Because our hypothesis here is H0, theta 1 equals 0, right? This is our hypothesis. That's why I'm talking about 0 here. So you can see that 0 is barely inside this interval. What does it mean? Let me go back to you. So basically 0 is inside this interval. What does it mean? At which significant level? Okay, let me go back here. 5%, right? Because the confidence interval, they use the 5%, which is 1.96. Okay, this confidence interval is calculated based on the 5% significance level. That's why in this case, 0 is still inside this interval, which means we cannot reject the hypothesis at 5%, but we can reject it at 10%. Okay? So be careful which significance level. And last sentence said that this method, creating a new variable to turn a 2-coefficient hypothesis into a 1-coefficient test, always works, okay, always works for any hypothesis about a single linear combination of parameter, very general, very useful technique. Keep it in your toolbox. Next one. Before we talk about T-ratio, which is the individual hypothesis testing. But right now, we want to test multiple linear restriction. So we need F-test, all right? F-test. This is for multiple, okay? Be careful, multiple. Let's see the example. Basketball player's salary, log salary, equal beta 0 plus beta 1, years plus beta 2, average number of games per year, plus beta 3, batting average plus beta 4, home runs per year plus beta 5, runs batted in per year plus mu. So this is the interesting question. Do performance statistics matter at all? Remember, okay, start with your question. This is the question that we want to know. Based on this question, we need to have your own hypothesis, which is H0. Okay, so once we controlled the year in the league, this is the control variable, okay? That means we want to test 3 coefficients simultaneously. What does mean simultaneously? At the same time, okay, at the same time. So in this case, our H0 becomes beta 3 equals 0, beta 4 equals 0, and beta 5 equals 0 against our alternative hypothesis. H0 is not true. Test whether performance measures have no effect, okay, or can be excluded from the regression. Let's say if we want to drop those 3x, right? So this is our hypothesis. The question is, why can't we just run 3 separate T-ratio there? Because the answer, if you test, okay, let me show you the estimation results, okay? Okay, so x1, x2, actually this is x3, x4, x5. Those 3x is the one that we want to test. If you calculate the T-ratio individually, it's easy, right? You use the coefficient divided by standard error. You will find that none of them is significant if we test them individually. Okay. Because if we use the T-ratio, the question becomes 3 separate questions, right? Is bad significant? Is hours of this one significant, etc., each ignoring the other two. What we actually want is one joint question. Remember, this is the joint question. Do those 3 variables together add anything to the model, add any new information to the model? That's fundamentally different tests, okay? And it needs a different tool, which is F-test, right? We need F-test for testing the multiple linear restriction, right? So let's see here. Can you check the 3x T ratio? Can you tell me your answer? I'll give you 2 minutes. So please calculate the T ratio for each of those 3 variables. And here we have our observation. SSR. What is SSR? Notice the SSR, okay? Sum of squared residuals. We'll need this number in a moment. What is the T ratio for each? Okay, have you got your answer? What is the T ratio? 0.89. And next one, 0.89 as well. The third one, 1.5. So you compare with the critical value, you see that even at the 10%, our critical value is 1.645. So each of them, we cannot reject, okay? We cannot reject our null hypothesis. So which means individually, those three variables are insignificant, okay? But individually, okay, so here I need to remind you, okay, here is the unrestricted model, which means the full model. We didn't put any restriction. So unrestricted means the full model. And the SSR, please label it unrestricted, okay? So this is the SSR for the unrestricted, all right, which is 183 something. Next one. Here is restricted. Why restricted? Because remember our hypothesis. H beta 3 equal beta 4 equal beta 5 equal 0, right? And then we put those restrictions into the model, which means beta x3, x4, and x5 disappears, right? We restrict it to be 0. This is the restricted model. Because this is our restriction. Our null hypothesis is our restriction. Let me copy it. All right. We restrict beta 3, beta 4, beta 5 equals 0. This is the idea. So here you need to know the unrestricted model, which is the full model, the restricted model, which means we put our hypothesis into the full model, right? Restrict them to be 0. So this is the restricted model regression output. We have new SSR, and this one is the restricted, okay? Please label it restricted. Maybe here I need to on-R, follow, let's to be the same. This page showed you the SSR, which is unrestricted model. And here showed you the SSR for restricted model, okay? Notice that from 183 to 198, the sum of squared residuals necessarily increases, right? But is this increase statistically significant? Why it increases? Because with removing variables can only make fits worse or equal. That's why our sum of squared residual is higher, right? So the real question is that, is this increase big enough to matter, or just small, or just random noise? That's exactly what F-test measures, okay? F-statistics measures. Let's see the formula. This is the formula. SSR restricted minus SSR unrestricted. And this is number of restriction. How many? We have beta 3, 2, 1, right? 1, 2, 3. We have 3 restrictions, right? That's why Q equal 3. We have 3 restrictions. In the numerator, let's see the denominator. SSR unrestricted. Follow the degree of freedom, which is n minus k minus 1. And this F statistics follows the F distribution. All right. Have you learned F distribution? Let's see the relative increase of the sum of squared residuals when going from H1 to H0 follows a F distribution. Quick look at the shape of this F distribution, okay? And then our rejection rule. Notice that unlike the DT distribution, the F distribution is only positive. Okay, this is the F distribution and it's only positive. Makes sense. F is built from SSR increases, and SSR can only go up or stay the same when you drop variables, okay? Never negative. So F is never negative either. That's why our F distribution is only positive, okay? Same logic as before, okay, for the rejection region. Since large F means restrictions hurt the feet a lot, okay? So we only reject in the right tail. F is a one-sided test by construction. Even though H1 itself isn't directional in the usual sense. So let me write down the decision rule. If you get big F statistics, okay, that means restrictions hurt the feet a lot. In this case, we reject our null hypothesis. And if it's small, which means dropping them barely change anything. So in this case, we don't reject. We cannot reject H0. This slide, we pick the 5% significance level, okay? And at 5%, the critical value is 2.76, okay? So the rule is that we reject H0 if F is greater than 2.76. Okay, let's move on here. So now we have the formula, right? So let's see how we calculate the F statistics. You just plug in real numbers, right? SSR, what is this? SSR restricted, right? Let me go back. You see? This one, SSR restricted. Let me copy this formula. Okay, so you just plug in numbers, right? And I told you 3 restrictions. That's why here is 3. And then this is number of observation, n minus k. K is number of x. Minus 1, this is the intercept, beta 0. Right, this is the degree of freedom in the unrestricted model. This means our F follows F 3, 347, right? 3 is in the numerator and this is from the denominator. Be careful, otherwise you will be confused. And in this case, we use the critical value, which is at 1%. At 1%, the critical value equals 3.78. And our F statistics, which is approximately equal 9.55. Right? You see that 9.55 is way bigger, right? Bigger than our critical value. Which means it falls in the rejection region, right? Because 9.55 is much bigger. So in this case, our p-value will be extremely small, close to 0. This means the null hypothesis is overwhelmingly rejected. We have a strong evidence to reject H0, all right? Okay, so let's see the discussion. Now, connect this back to what we saw 2 slides ago. This is the key insight. Remember our 3 variables. Okay, our 3 variables, those 3 were not significant individually, but they are jointly significant. How can both be true? Think about it, okay? Jointly significant. So the likely explanation is that those 3 X may have multicollinearity, right? Because those 3 variables are highly correlated with each other. Good hitters tend to score higher on all 3 at once, the other 2 around, right? So those 3 variables are highly correlated. That's why if we test them individually, we cannot isolate each of their individual effects. So individually, they are insignificant, but jointly, they are significant. All right? T ratio fails. F statistic works here. Same as in your paper, okay? If your X are high correlated with each other, don't drop them too fast. Okay, in microeconomics, we have Owen price, substitution price, right? Basically, those 2 variables, they are highly correlated. So you cannot reject them and you cannot test them by T ratio, right? Think about it. Another suggestion is never conclude a group of variable doesn't matter just from individual t-tests. Always check jointly with an f-test, okay? Especially when variables are highly correlated. Anyone has tissue? Can give me 1 tissue? Thank you. I'll let you digest. Let's continue. I'm gonna finish chapter 3 today, okay? So this is in general. Let's see here, in general. And also this is a special case of the f-test, okay? So here, suppose we want to test all slope coefficients at once. This is our regression, beta 1 through beta k, right? Those are our slope. Remember slope? So our hypothesis H0, beta 1 equal beta 2 equal all the way through to beta k equals 0. This means none of our x variables help explain y at all. Even slope, okay, every slope is 0. That's why I showed you the null hypothesis states that the explanatory variables are not useful at all in explaining the dependent variables, okay? Which means all x, none of our x helps. And then we restrict, this is the full model, right? This is the full model because no restriction, unrestricted. And then if we restrict it each slope equals 0, here we got our restricted model, which means regression only on constant, which is beta 0. So in this case, our F statistics becomes R squared and over our kx, right? In the denominator is 1 minus R squared, okay? Then this is the degree of freedom. And this is the F distribution, follows a degree of freedom of k and n minus k minus 1. So this one, we can only know R squared, right? And then we can calculate the F statistics. That's why this is much easier to compute, okay? No need to run two separate regressions. Before, right? Before, in order to test, we need to run first the unrestricted model, which is the full model to get the SSR. This is once. And then we run the restricted model again, which means we need to run at least twice to get the restricted SSR, right? But in the spatial case, right? In the spatial case, we just only run once, okay? And then we get R squared. So you can get the F statistics as well. This is called the test of overall significance, okay? The overall significance. And every regression package reports it automatically. Every time you run a regression, you get R squared for sure. In practice, it's usually overwhelmingly rejected, all right? The meaning is that your X variable jointly explains something of your Y, even if small, okay? This test is the lower bar, like the benchmark. It doesn't tell you your model is good, just that it's not completely useless. It's not completely useless. Okay, so this is our last example. The F test can handle more general restrictions, not just equal 0. Look at this example. This is our model. Log price equal beta 0 plus beta 1, log assessment, okay? The assessed housing value before the house was sold, plus beta 2 log size, right? Plus beta 3 log square footage, and beta 4 number of bedrooms, which means that's why this is the general, okay, general linear restriction. So the question is that, are house price assessments rational? Let me write it down. Let me remind you again, you always start with a question when you want to write a paper. Even you just answer 1x, it's fine. Even you just answer 1x is fine. So here, our house price assessment rational. If assessors do their job well, a 1% change in assessed value should predict exactly a 1% in actual price, okay? No more, no less. That means our beta 1 should equal to 1, right? And once you know the assessed value, other characteristics like lot size, square footage, bedrooms shouldn't add any extra information about price because it's about assessment of the house. So which means our hypothesis is beta 1 equal 1 and beta 2, beta 3, beta 4, they are 0, right? This means we can use F test to test this one as well. Okay, before I showed you our f-test, all of the betas are equal 0. But right now, we can use it to this general. Any restriction you want to test, okay? So here, our restriction sets a coefficient to a specific non-zero value, which is 1. The other to 0. This shows the real power of the f-test, all right? It can test any combination of linear restrictions at all once, not just simple exclusion test, not just 0. Let me write it down. So f-test, it can test any combination of linear restrictions f-test is very powerful, okay? Mechanically, it works exactly the same way. Estimate restricted versus unrestricted model, all right? So you run the regression twice, you compare the SSR, and then you compute the F statistics, right? The same formula, same logic, just a more interesting hypothesis behind it. Okay, let's see. Let's see the regression. Next one. Let's see how to actually build the restricted regression for this hypothesis, okay? Suppose our unrestricted model, which is the full model, right? Beta 1 through beta 4, this is the full again. And then, and here, x1 basically equal to log assessment, right? And so on, beta x2, x3, x4. And now we impose our h0. What is our h0? Let me copy it. Paste here. All right, let's see. Let's see the restriction. If we put our restriction into the full model, the model becomes right. This is our restricted model. And then we can cancel out some terms, which is x, this one, and this one. That's why finally we have our restricted regression, which is y equal beta 0 plus x1 plus mu. And then you rearrange it, okay? You move x1 to the left side, you'll get y minus x1 equal beta 0 plus mu. So the restricted model is just a regression of a new variable. This is our new variable, y minus x1. The restricted model is actually a regression of y minus x1 on a constant. Because we have only beta 0 here, right? Okay, the same trick idea as before. Build the regression directly into a transformed variable and we run a simple regression, get SSR restricted. I'll show you those SSR restricted and SSR unrestricted, okay? Same here, we have 4 restrictions, right? 4 restrictions. Beta 1, 1, 2, 3, 4. That's why we have 4 restrictions. This is n minus k minus 1. And if we plug in numbers, we will have our F statistics, which is approximately equal 0.661. What does it mean? And we take the critical value at 5%, which is 2.5. Okay, so here, this one is less than 2.50. So basically, our null hypothesis cannot be rejected. What is the conclusion? Conclusion means that the data is consistent with rational assessments. Okay, the conclusion is that the data is consistent with rational assessments. We don't have evidence against beta 1 equal 1 and the other 0 jointly. We don't have evidence to reject our H0. Okay, we don't have. Next one, okay, this is the regression output. And also the last slide of this chapter. Okay, I'll give you 3 minutes. This SSR is the unrestricted, right? Because this is the full model. Let's see, here is the regression output. We have log price hat equal beta 0 plus beta 1 plus beta 2 minus beta 3 plus beta 4. You have n SSR unrestricted here, right? So basically in the exam, I'm going to show you the regression output for 2 regressions. One is for full model, unrestricted. Another one is for restricted, okay? You should be able to compute this one. You should be able to compute F statistics and compare with the critical value. Of course, I'll give you the critical value. You should be able to do the hypothesis testing. Let's see the coefficient on log assessment is 1.043, which means close to 1, right? Remember our hypothesis. Okay, and if you look at the other 3, beta 2, beta 3, beta 4, the same story for the other 3, okay? Each individually close to 0, right? Close to 0, close to 0, close to 0. That means if we use individual t-test, we wouldn't reject beta 1 equals 0, okay? Each individual close to 0 and insignificant. If we use t ratio here for each variable, they are insignificant. So even one at a time, nothing here contracts rational assessment. This matches what the joint F-test told us. Okay, two closing points for this chapter. The first one, the F-test works for general multiple linear hypotheses. Whatever you have beta, let's see, beta 1 equals 0 and beta 2 equal 1, and then beta 3 equal beta 4 equals 0. Okay, so I just changed a little bit about our null hypothesis, okay? Any other linear combination, F-test can deal with it, can deal with that. It handles any combinations of linear restrictions, okay? Equalities or specific values, whatever your hypothesis needs. Now, last one, okay, second point, and very important. This is a warning. Every test and confidence interval we built this whole chapter relies on multiple linear regression assumption 1 through 6. They must be assumed true. Okay, we must have those assumptions. If those assumptions are violated, especially normality or homoscedasticity, our t-test, f-test, confidence interval, p-value, they may be wrong, all right? Not just less precise, but this is why we spend so much time up front discussion when normality does and doesn't hold. That's why we took a lot of time to talk about the assumption, right? So this is very important. And I'm done from my part. Next Tuesday and Thursday is the holiday, so we don't have the lab and we don't have the class on Thursday. Okay, next Wednesday and Thursday only. We'll meet each other next Monday. Okay, next Monday. So if no question, thanks for coming. I'll see you next Monday. Plan your trip to somewhere else for your. Well, maybe I know you guys I know you guys are thinking maybe we shouldn't have class on Monday. Next Monday. Really? Really?